Section: Introduction. In this section, we often embed discrete entities by mapping them to dense real-valued vectors. For example, words are embedded based on their context in a large language model, and recommender systems learn embeddings of items and users based on user interactions. These embeddings have various advantages. They can be used directly as inputs for other models or to measure similarity between entities that were previously distinct. Cosine-similarity is commonly used to measure semantic similarity between entities. Larger cosine-similarity values indicate closer proximity, and it has become a popular measure for this purpose. However, while many papers have shown successful applications of cosine-similarity, it may not always work as well as other methods like the dot product between embeddings. We aim to explain these inconsistent findings. We discovered that cosine similarity of embeddings can produce arbitrary results due to the flexibility of learned embeddings. This issue arises because the embeddings can have a degree of freedom that allows for arbitrary cosine similarities even when their dot products are well defined. To gain more insights, we derived analytical solutions, focusing on linear matrix factorization (MF) models, which we will discuss in detail in the next section. We also propose potential solutions in the following section. Our experimental results further support the findings presented in this paper. In this paper, we concentrate on linear models because they offer closed-form solutions, providing a theoretical understanding of the limitations of using cosine similarity with learned embeddings. In matrix factorization (MF) models, the goal is to estimate a low-rank matrix by multiplying two lower-dimensional matrices. These matrices represent item and user embeddings in the context of recommender systems. The model is based on the dot product between user and item embeddings, even though cosine similarity is commonly considered after the embeddings are learned. The effectiveness of cosine similarity is influenced by the regularization techniques used during the embedding learning process. We discuss two common regularization schemes in the following sections. These schemes differ in how they apply L2 norm regularization to the embeddings. The first scheme, which involves regularization on the product of the matrices, has been found to perform better in terms of prediction accuracy compared to the second scheme. Additionally, the first scheme is invariant to certain transformations, leading to unique solutions. Overall, our analysis highlights the importance of considering the impact of regularization techniques on the utility of cosine similarity in measuring similarity between learned embeddings. Section Summary. Introduction. In this section, we explore how discrete entities are transformed into dense real-valued vectors through learned mappings, such as in language models for words and recommender systems for items and users. While cosine similarity is commonly used to measure semantic similarity between these embeddings, we reveal that it can lead to arbitrary results due to the freedom in learned embeddings, which can render cosine similarities arbitrary even when dot products are well defined. Our focus on linear matrix factorization models allows us to derive analytical solutions and propose potential remedies to address these inconsistencies. Section. Details on first objective, EQ. 1. In this section, we tackled the first objective as described in equation 1. We found a closed-form solution for the training objective in equation 1, which involves matrices and singular value decomposition, SVD, of the data matrix. The matrices U and V contain the left and right singular vectors, while sigma is the diagonal matrix of singular values. When considering the k largest eigenvalues, we use truncated matrices of rank k denoted as U_k and V_k. When exploring the cosine similarity in the context of a full-rank MF model, when k equals p, we made some interesting observations. For instance, if we choose a specific matrix D, the cosine similarity between different item embeddings turned out to be 0, implying that items are only similar to themselves. On the other hand, the user-item cosine similarity remained unaffected by certain choices of D, resulting in the same item ranking based on predicted scores. By making different choices for matrix D, we observed varying cosine similarities, highlighting the arbitrary nature of the results. Despite the model being invariant to D, the cosine similarity outcomes are not unique. This demonstrates that the cosine similarity results can differ based on the chosen parameters, emphasizing the variability and lack of uniqueness in this model. Section Summary. In this section, we derive a closed-form solution for the training objective using the singular value decomposition, SVD, of the data matrix. We explore the impact of different choices for the matrix D on cosine similarities, revealing that the results are arbitrary and not unique, emphasizing the non-uniqueness of cosine similarity in this model. Section. Details on second objective, EQ. 2. In this section, we tackled the details of the second objective as defined in equation 2. We derived the solution for this objective, which involves the singular value decomposition, SVD, of the training data. The key difference from the first objective is that the L2 norm regularization is applied individually to each matrix, making the solution unique. This uniqueness is important as it ensures that the cosine similarity applied to the learned embeddings of this matrix factorization, MF, variant gives distinct results. We also explored remedies and alternatives to using cosine similarity. One approach is to train the model specifically with respect to cosine similarity, which can be facilitated by layer normalization. Another strategy is to project the embeddings back into the original space before applying cosine similarity. It's worth noting that normalization in cosine similarity is typically applied after the embeddings have been learned, which can impact the resulting semantic similarities. Furthermore, we discussed various techniques such as standardizing the data, negative sampling, or inverse propensity scaling to address issues like popularity bias. These methods can enhance the quality of semantic similarities in practice. Additionally, we highlighted the importance of considering different item popularities and user activity levels in the learning process. Moving on to experiments, we conducted simulations on low-rank embeddings to investigate semantic similarity metrics. By generating interactions between users and items grouped into clusters, we examined how well cosine similarities applied to learned embeddings can capture the item cluster structure. The experiments involved generating simulated data, learning matrices A and B from the data, and analyzing the item-item cosine similarities under different scenarios. These experiments shed light on the impact of training objectives on the resulting cosine similarities and emphasize the need for careful consideration in model training.